Up to now, we have covered the unforced vibrations, that is the response of systems to initial conditions, free vibrations, that is. At this point, we will be looking at the forced vibrations, and the fundamental force kind of forcing we will be looking at will be the harmonic forcing, in which you will have a sinusoid forcing on a 2 degree of freedom system. So you have two masses, and there might be possibly two kind of forces on each mass, but the forces are of the same frequency omega. If the forces are of different frequencies, you can use the principle of superposition, but let's leave that for the time being. Now, the equation of motion of the system will be mx double dot plus kx is equal to f sine omega t, where f is the force vector with the amplitudes of f10 and f20. Again, we try a harmonic solution. U is x1 and x2. So x double dot will be the square minus omega squared multiplied by x itself. So you substitute that into your equation and you get the following equation. Now, if you remember, in the unforced case, the right-hand side was 0. Here you have an f. Okay. Now, it is possible to solve this. This is a matrix equation that contains the frequency term omega inside it. Let's call this matrix Z of omega, which is called the impedance matrix. Impedance matrix is a matrix that describes the system but is a function of frequency. As the frequency changes, the impedance changes. Now, you can write therefore your equation as follows. Z of omega times U is equal to F. Therefore, the U, which is the vibration amplitudes of the system, like maybe I should write it down. U is equal to x1 and x2 being the amplitudes, can be solved by inverting the impedance matrix and multiplying by the force. If you invert a matrix 2 by 2 matrix, the inverse of a matrix is the adjoint divided by its determinant. And the determinant of Z of omega is simply the determinant of minus omega squared plus m, well, omega squared m plus k. And remember that equating this to 0 gives you the characteristic equation of your system, from which you can find the natural frequencies of the system, so that when the determinant of minus omega squared m plus k equals 0, you are going to have a resonance in which the amplitude of the motion is going to be infinite. So in the forced vibrations case, if, let me write it down here, if, let's say, omega equals omega 1 or omega equals omega 2, you will have x will going to infinity, x1 and x2 going to infinity, and that we call the resonance, as you know. Okay. So if you force a system at its natural frequency, the amplitude will be infinite. Let me give you an example here. Let's say that you have a 2 degree of freedom system with the first mass is forced, the second is not. So F1 is F1 0 sine omega t, F2 is 0. The impedance matrix is minus omega squared m plus k is the following matrix. Okay. It's you find that again x from u sine omega t, let's say, u being, as we said before, u is equal to x1, the amplitude of the first mass and the second mass. U is equal to z omega inverse times f. And you can solve this by inverting the following matrix. 2 by 2 matrices are easy to invert. You just change the signs of the off-diagonal terms and replace the diagonal terms with each other, and divide it by the determinant of z. The determinant of the impedance matrix is equal to this quantity. If you equate it to 0, you find the natural frequencies of the system. And if you remember, The natural frequencies were k over n and 3k over n. So if you multiply this thing and divide by the determinant, you get the following equation, solutions rather. The first mass, amplitude of the first mass is going to be this thing. This whole thing will be x1, and this whole thing will be x2, okay? So the amplitudes go to infinity at the resonances, and at some values they have different values. Let's look at it. For example, x1 plot over the frequency. This is a frequency response plot. x1 goes to infinity when omega equals omega 1 or omega equals omega 2. And in between somewhere, the amplitude of x1 is 0. And then, as you see, after the first natural frequency and the second natural frequency, the phase shifts by 180 degrees. This is the response of the first mass. The response of the second mass also goes to infinity at the resonances, and it has a phase shift in between the resonances, but it doesn't cross the 0 point. So this is the plot of the frequency responses, plot of these terms, that is. Now, from here, it is inappropriate that we talk about vibration absorbers, because the vibration absorbers uses exactly this idea. It's basically a 2-degree of freedom system in which you have a machine or a vibrating system which is forced by let's say, a harmonic forcing, and it might be vibrating quite violently because it's close to the resonance, and you connect a second mass to it and let it vibrate. If you tune that vibration absorber correctly, it can absorb the machine's vibrations and let itself vibrate, so that the vibrations of the main system is going to be decreased. And this is a very common thing to be used in applications. For example, you have used the reciprocating tools, sanders, saw, compactors, etc. Lots of engines might use the idea of the vibration absorber, but one disadvantage is that the speed of the operation should not be varying too much. If it varies a lot, in that case, vibration absorber might not be too effective. Let's analyze this. Let's say that this is your machine, which you have M1 is the machine mass, M2 is the absorber's mass. Absorber is connected to the main system by a spring, which is K2. The equation of motion is as follows. So you want to find a harmonic solution, and we do exactly as before. We find the impedance matrix. We find that U, which is x1, x2, is equal to Z inverse of omega times F, F being this thing, down the right-hand side, okay? And from here, we find the solutions. This is x1 solution, this is x2 solution. x2 is the vibration absorber amplitude, x1 is the amplitude of the main mass. And we notice something in the numerator. If K2 minus M2 omega squared, this term, is equal to 0, well, what do we see? In that case, the vibration of the main mass is going to be 0. That is, this mass is going to have 0 vibration, okay? All the vibration is going to be transferred to this second mass, okay? And that will not be vibrating at resonance or anything. It will just be vibrating at a certain frequency. So if you select K2 and M2, which are your absorber parameters, such that it is equal to the forcing frequency omega squared, K2 over M2 is equal to omega squared, in that case, your main mass is going to have no vibration. And on the other hand, if your main mass and spring system had a resonance close to the operating frequency, in that case, you would be designing your absorber so that K2 over M2 is equal to K1 over M1, which is equal to omega square, which is equal to omega n square. Okay. In that case, instead of being close in the resonance, the main machine will have zero amplitude, zero vibration, theoretically at least. And the main mass vibration, as you see, is going to be F0 over K2, okay? Which is, as you see, it is in this equation, it is K2 F0 divided by K2 square, where this K2 minus M2 omega square, this term becomes a 0. So you have minus K2 minus F0 over K2 as your amplitude for the second mass. It will be vibrating out of phase with your forcing. It is quite a useful thing to do. So you tune your absorber so that its natural frequency of your absorber only matches the forcing frequency. That's how you design your absorber. And if you look at the frequency response, if you select the delta static to be F0 over K1, this is the definition of static deflection. And if the first resonance frequency, first frequency of your machine already, resonance frequency, as a single degree of freedom system, if it's K1 over M1 to the square root, this is not very easily understandable. Let me write it here. This is square root of K1 over M1, actually. If you do that, the initial frequency response would be this one. Okay, as you see, this is an undamped system, so it goes to infinity. 1 degree of freedom system without the absorber attached will have a resonance at 1. Okay. Now, if you attach a resonance at that frequency, at the frequency of 1, at the frequency of the natural frequency of the system, and the natural frequency of the absorber is the same as the natural frequency of the system, you will have a 2 degree of freedom system like this one. It will have 2 resonances now, but at the original resonance, you will have a 0 vibration. Okay. So, using the idea of forced vibrations, we will be able to design absorbers which drive the amplitude of motion of the main system to 0. And we will be using this concept later on for absorber design. Let's leave it here at this point, but we will look at the absorbers later on during the course.